Now we look at a more involved example. This example is the premises P implies Q or not R, and the Q implies P and R, and the conclusion is P implies R. To check this, if this argument is valid or not, we can use the truth table method. But this truth table is more complicated because we have 3 variables, P, Q, R, and therefore we build a larger truth table. Because we have 3 variables, there's 8 columns, 8 rows. So we have this P, Q, R, 2, 3, 4, 5, 6, 7, 8. Okay, and T, 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 F, 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 T, T, F, F, T, T, F, F, T, F, T, F, T, F, T, F. And our next column is not R. Q or not R. P or P and R. And you can easily check this column should be FT because it's just the opposite of previous column. FT, 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 FT. And this is a Q not Q or not R. So is all of these 2 columns. So it's a T, T, F, T, 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 F, T, and P and R is so TF, TF, F, 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 F. Okay, now we come to compute the truth value of the premises. So first one is P implies Q or not R. So what do we, usually how do you do this? Is you rename this because we already compute this. That's why we pre-compute this. We give it a special name. Let's call it X. So what this is, remember, this is nothing but not P or X. Okay, and therefore we can that make our job much easier. So the next one is Q. Let's write this Q2. Q implies P or R. And this I'm call this because this is just a column of our premises. And finally the conclusion. This is the conclusion, which is a P implies R. Okay, so now we come back to not P or X. Remember, for not P or X, we in the first 4 rows, because P is true, so not P is false. So we only need to read these 4 rows of X. So it's TT, TT, FT. And for the following, for the last 4 rows, because P is F, so not P is true. Therefore, this is automatically true. This exactly this implication truth is true by default. So TT, TT. And this one is similarly, we just rename it Y. So this is a Q, not Q or Y. And therefore we just, for first 2, we read Y, which is TF, and the next 2 automatically true. And then we read Y, which is FF, and the last 2 are true, automatically true. Let's see, not Q. Yeah. Okay, now we come to the place, remember, of finding the critical rows. Remember, the premises is just the second last and the third last column. And therefore, we only need to verify both of these 2 columns have truth value true. So that means that we only need to check this row, this row, this row, and this row. We only need to check on these 4 rows. That means we don't need to bother to compute the truth value of P implies R for the other 4 rows. So remember, P implies R, which is equivalent to not P or R. And for this one, not P or R, that means this is R because P is true. So this is true. And for this one, not P or R, this is false. And for this one, and this, remember, this is true by default. And so basically we are done. What's our conclusion? Our conclusion is this one. If the argument is valid, we should have true, 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 true. We should have the truth value of each of the conclusion in the critical row should be true. But then we find that there is a false. So that means argument is invalid. So let me show you another way to see this. So remember, the premise, there are 2 premises. The first premise is P implies Q or not R, because you have this all relation. That means you can either implies Q or implies not R. And when you can implies Q, if not R is false, then you must implies Q. If not R is true, then it may implies Q and may not implies Q, and the same thing for R. Okay. So we have 2 branches. Let's check the first branch, P implies Q branch, and then we have Q implies P and R. So P implies Q implies P and R. That means we in this branch we have P and Q and P repeat again. So we don't need to say this. We can get rid of this P. So we have in this branch we have PQR. So that means no problem. We have P implies R. That's correct. However, on this branch, we have this P implies not R, but our conclusion is P implies R. So we have, assuming P, we have both R and not R, and this is called contradiction. And some people use the notation like this. They have 2 arrows colliding with each other. So the conclusion, contradiction. And you can see why we have this Okay, sorry. So this show that this argument is invalid. So where can go wrong? The only place it can go wrong is P is true, but Q is false. And then this, then the premise is premise P implies Q not R will force R to be false. Okay, therefore P implies R is false. And you can see in this critical row here, in this row, it's just we have P is true, Q is false, and R is false. So exactly in this setting, the argument doesn't work. Okay, let's move to the next page. Let's look at some important argument form. So this form are very important and also has been developed probably more than 2,000 years, because I think this argument form was developed in ancient Greece. So the so such a form called syllogism. Don't need to worry about this. What the meaning of this? I think roughly the meaning is you have two premises and then you have conclusion, and also there are some overlapping between the premises and the conclusion. Anyway, this is a very special terminology. You don't need to worry about it. So both of these are called a form of syllogism. So we have major premise and a minor premise. And then we have one conclusion. So the first one is called Latin, the name is a Latin name, is called Modus Ponens. It's, so the Latin name is method of affirming. So the name may sound strange or foreign, but the form is very trivial. It's just if P, then Q, P, therefore Q. The example is also trivial, very simple. It's the example here is if today is Easter, then tomorrow is Monday. And of course, today is Easter is our P, tomorrow is Monday is our Q. And then we have today is Easter, and therefore we have tomorrow is Monday. Okay, this is a Modus Ponens. And another form is also very important and very simple. It's called a Modus Tollens. The Latin name is the Latin name for the Latin meaning of this is method of denying. And the form is look like this: if P you have the first premise is if P then Q, and the second is not Q. So what can you infer from this? Then you must have not P. And this is very simple because it's also straightforward because you can either, you must have either P or not P. But if you have P, and then by the first premise, you have P then Q, and will contradict with not Q. Therefore, you must have P. Sorry, you must have not P. So the example of Modus Tollens is we still have the first, if today is Easter, then tomorrow is Monday. And then the second one is tomorrow is not Monday. What we can conclude? We can conclude that today is not Easter. It's very straightforward. So we have Modus Ponens and the Modus Tollens. Okay, let's next we are going to look at additional valid argument form. Additional rule of inferences. So the first rule is called the generalization. All these rules are very straightforward, and it's just something you use every day. And this we just here give you a name and make it more formal and more rigorous, so that you you will be aware of which rule are you using when you construct your argument. So the generalization is if we have P, and therefore we must have P or Q. And similarly, if we have Q, we can infer that Q or not P or not Q, P or Q. Which is trivially true, right? The second one is specialization. If I know, if I assume that the P and the Q, what do I know? And definitely I know that P and the Q must both hold. Therefore, specialized to P hold. Similarly, if I assume P and the Q specialized to Q, Q hold. And C is conjunction. So if I assume P and I further assume Q, and therefore trivially have P and Q. And the fourth one is called elimination. Elimination means we have two branches. If you know one branch is dead, then you have to go to the other branch. So basically, if you have P or Q, you assume that you assume P and Q. You further assume not Q. Then you can conclude that therefore you must have P. And similarly, you have P not Q, P or Q, and you know that not P, and therefore Q. And the next one is called the transitivity. And we have P, if we have P implies Q, And also we have Q implies R, and therefore we have P implies R. And the sixth one is called proof by division of cases. By division into cases. The argument form is we assume P or Q. We know, and also we assume that P implies R. We also have Q implies R. And therefore we must have R. So we have two cases, either P or Q holds. And we check that P, if we assume P, then R holds. Okay, that doesn't conclude R must hold because you haven't checked the case of Q. And then if you further check, Q also implies R. And then you conclude that R holds. By the way, all these argument rules, argument form are valid, and you can check this fact by just write the truth value. I'm sorry, use the truth table method. It's straightforward, but sometimes can be tedious. And the last one is a very interesting and very useful one is the contradiction rule. I especially mention this contradiction rule. So we have, if I assume not P implies contradiction, and then we must have P. And let me just quickly give you a quick proof why we have this, because not P implies C. What does this mean? Remember, it's logically equivalent to P or C. And by our, I forgot what the name of this, but whenever you always you have a proposition and always a false value, and then the value is itself. And therefore we can see that the assumption that not P implies C is logically equivalent to P. Okay, next we are going to see two examples of how to get the okay, the first example is example 2.3.a in textbook. It's a very long paragraph, so I'm not going to write everything here because, but and for student haven't purchased the textbook, I'm going to briefly sketch. I'm going to read the problem and write the abbreviation. So this example is you are about to leave for school in the morning and discover that you don't have your glasses. You know the following statement are true. A is if you are reading a newspaper in the kitchen. If I was reading the newspaper in the kitchen, then my glasses are on the kitchen table. So we are going to write this as reading in the kitchen, and we're going to write this RK implies GK, glass on the kitchen table. And B is if my glasses are on the kitchen table, then I saw them at breakfast. So then the second one is GK. All these are premises. And saw them on the breakfast, saw them at breakfast, SB. And C is if I didn't see my glasses at C is I didn't see my glasses at breakfast. So simply not SB. And D is I was reading the newspaper in the living room, or I was reading the newspaper in the kitchen. I read a newspaper in the living room. We would denote this by RL, or RK, reading in the kitchen. And E is if I was reading the newspaper in the living room, if RL, then my glass is on the coffee table. Glass on the coffee table. And the question is, where are the glasses? The solution of this is we just A, B, C, D, E are our premises, and we were trying to get a conclusion. So we have RK implies GK, GK, and usually what you do is you just write this RK is in your knowledge, and also you know GK. If RK in the sorry, let's try this way. I think we are not going to use that form. So we have RK implies GK because GK implies SB, and by the transitivity we know that RK implies SB, and because we know that not SB, and what we know by the contradiction rule, we know that not RK. Okay, then we have RL combined with RL or RK. What does this mean? So this combined implies by let me see the rule of what is the name of the rule? The name is elimination. Let me just write RK implies GK RK. This is by transitivity. And then we implies not RK, and this is by Modus Tollens. And this is by contradiction. RL, this is by elimination. By elimination, we know that RL. And then we have RL, combine this RL to GC. And this is, we have our conclusion is GC. And this is by Modus Ponens. Okay, this is the complete, the first example. Let's look at the second example. The second example is example 2.3.14 in the textbook. And this one is short. This example is short, so I'm going to write the detail on this board. So on an island, on a fictitious island, and there are two kind of people, knight and the knaves. And the property of night, and the night always tell the truth. And it's always lie. And one day you are on the island and encountered person A and B. So person A said B is a knight, and then person B said A and I are of opposite type. So the question is, what types are A and B? To solve this problem, you use the contradiction rule. Okay. General strategy is apply the contradiction rule. So you suppose, for the sake of contradiction, suppose A is a knight. Then what we can infer? So remember, A is knight. If A is a knight, then A always tell the truth. And then what A said B is a knight. And therefore we can infer that B is a knight. And then from B, because B is a knight, B always tell the truth. And what we can infer, we can infer the truth is A and B of opposite type. What did we get? We reach a contradiction because we know that we assume that A is knight, then we get B is knight, and A and B are opposite type. And of course, this is absurd. There's a contradiction. So we reach a contradiction. That means our assumption, of course, our argument is a valid argument. So the only possible problem is our assumption. So our premise A is a knight is wrong. So we know that our conclusion is A is a knave. Okay, then similarly, we assume that suppose B is a knight. Then what? NIGHT. Suppose B is a knight. Then what do we get? Suppose B is a knight, and then what we get is A and B are of opposite type. Then what? That means because B is a knight, he always tell the truth. Then we have A and B of A and B are opposite. And because B is knight, that means A is knave. And what he said is must be a lie, and that means but he said B is a knight, so that means B is a knave. And we reach contradiction again. That means our assumption that B is a knight is wrong again. And therefore our conclusion is B is a knave. Okay, so basically we have solved problem. You may wonder what happens if I assume that A is a knight, A is a knave. It's a knave. The solution, the answer is you won't reach any contradiction. You will get a consistent. You will get a consistent scenario. That means That means doesn't mean that your assumption is always correct, because maybe there's some contradiction and you haven't found it. Okay, but therefore you should the general rule is you assume something. If you find a conclusion, you find a contradiction, you can stop and then you reach your correct conclusion is your assumption is wrong. But if you assume something and you didn't find any contradiction, doesn't mean that your assumption is correct. Maybe it's correct, maybe it's incorrect, and you haven't found the contradiction. Okay, at the end of this video, I'm going to mention two common errors, common for fallacies of argument. So the first type of fallacy is converse error. The error is P, if we assume P and Q, and we assume Q, and you get P. And of course, this is wrong because P implies Q, and you also assume Q doesn't tell us anything about P. Let me give you an example. The example is if tomorrow is Saturday, then we don't have class. And the second assumption is we don't have class tomorrow. Can we reach the conclusion is that tomorrow is Sunday, Saturday? Of course not, right? Because tomorrow being Saturday is just a sufficient condition for not having class. Maybe tomorrow is Sunday, we also don't have class. Even tomorrow is Monday, if it's Martin Luther King Day, we don't have class either. So we definitely won't have this conclusion. The second error is called inverse error. Abstract form is a P implies Q and not P, then we reach the conclusion is not Q. Oh, by the way, this is wrong. And this is also wrong. Because not P doesn't say anything about Q. I don't know what happened. So in the same example, we have here if tomorrow is Saturday, then we don't have class. Tomorrow is not Saturday. So what can we infer? No, nothing can be said. We can have class, and we can and you reach the conclusion that we have class tomorrow. Which is all wrong. I think the fallacy and error are pretty clear. Okay, I'm going to stop here for this video. Thank you.